Take a breather and look up. The sky is a quiet library, and each point of light is a book with its own plot. We'll read slowly, like a stroll through a garden after rain. Here is one useful thought to pocket. You are made of star-forged atoms, arranged by cosmic history into a living pattern. That isn't poetry, it's chemistry with a long memory. When you sip water, you taste molecules older than continents. Knowing this can make ordinary moments feel a touch wider and kinder. We begin on a porch at dusk, with the kettle murmuring and the first stars peeking through. Imagine the universe as your neighbourhood, not distant but woven into every breath and sip. The steam from your cup curls like a tiny nebula, soft and silver, hinting that the grand patterns above echo in small comforts below. Why the universe matters is simple. It is the ground beneath every ordinary thing, the backdrop that turns daily life into a chapter of a larger story. Think of a loaf of bread. Flour, water, yeast, and time give it bounce, fragrance, and strength. Your life is a similar recipe. Particles forged in ancient stars, stirred by gravity, warmed by sunlight, and seasoned by time. The crust is your skin, the crumb is your mind, and the whole loaf sits on a table made by the Earth's orbit, under a roof built by the galaxy's slow spin. When we learn the universe, we learn the kitchen we've always cooked in. This curiosity also helps us see further than our own doorstep. When storms come, we can read the clouds. When news claims certainty, we can ask better questions, because science is a practice of listening carefully. The universe trains that listening. We hear the whisper of starlight stretch thin with distance. We notice patterns, like the way night cools the air, or how seasons tilt us gently through the year. Wonder becomes a habit, and habits shape character. It can be tender too. The idea that atoms in your blood once hid in the hearts of stars can ease a lonely hour. It says you belong. Not just to a place or a family, but to an unfolding that started before any ancestor spoke and will continue after our names are dust. We are not passengers, we are participants, small and alive, drifting on a vast current with oars made of questions. Practical benefits follow. Astronomy builds cameras that see faint signals. Those tools spill into medicine and Earth observation. Timekeeping from pulsars and atomic clocks guides navigation. The maths behind galaxies helps track traffic, weather, and markets. Curiosity pays its way, not because it must, but because careful attention is fertile. You water something, and roots find paths you didn't expect. There's a moral tilt here as well. The night sky is a shared ceiling, ignoring borders and ideas of us versus them. It suggests humility. When you look up, you're looking at the same light touching farmers, programmers, elders, and children everywhere. That doesn't solve disagreements, but it can loosen knots. We speak gentler when we remember we are tiny and temporary. Stories help us hold such largeness. The universe offers the biggest story we have, but it lands best in small images. A child chasing a moonlit moth, a tide curling under a pier, a phone screen reflecting a constellation through a smudge of fingerprint oil. These are places where cosmic and human meet, and the meeting is warm rather than cold. If this brought you a little calm, feel free to like and subscribe, and tell us where you're listening from and what time it is there. So the universe matters because it is not outside of us. It is the frame and the fabric, the kitchen and the loaf, the ceiling and the path. In the chapters ahead, we'll watch how space itself stretches like rising dough, how tiny early ripples became galaxies and cities, and how gravity is not a chain but a curve that guides motion. We will meet black holes that are less monsters than mirrors, showing us the geometry under everything. We will hold quantum hints lightly, like feathers you don't crush, and we will keep returning to the everyday, a hand on a railing, a window's rectangle of sky, the steady tick of a bicycle's chain. Speculative. Perhaps consciousness is the universe noticing itself through creatures like us. That thought is not a proof, merely a gentle possibility, like a bird settling briefly on a branch before flight. Whether or not it's true, awareness is our superpower. Attention ripens experience, and this shared attention to stars, to stories, to one another, can make the world we already have feel more spacious, more neighbourly, and more kind. Imagine a balloon with dots drawn on it. As you blow air into the balloon, every dot sees every other dot moving away, not because dots are exploding, but because the surface is stretching. Our universe behaves similarly, but in 3 dimensions. The fabric of space itself expands. The Big Bang was not a bomb in pre-existing emptiness. It was the beginning of the expansion, the start of space, time, energy, and the rules that join them. In the earlier scenes, the cosmos was a dense, hot fog. Think of a room filled with steam and glittering dust, where light cannot travel far without bouncing. As the universe expanded, it cooled, and those particles slowed enough to assemble into familiar matter. Protons, electrons, then atoms. That cooling is like steam turning into a clear morning, revealing a landscape that was always there, just hidden by haze. The phrase singularity appears in older tales, but we should be careful. It marks a place where our current equations break down, not a tiny pinprick of stuff in ordinary space. The better image is a rising loaf whose recipe begins with a strange batter. We don't yet know the exact starting step. Speculative. A complete picture may blend quantum ideas with gravity in a way we haven't yet learned. What we do know is written in light. As space expands, light's waves are stretched, like a slinky pulled gently. Distant galaxies glow redder than they would in a still universe. This redshift is not them racing through space, but space growing between us and them. When astronomers plot distance against this reddening, they trace a clean curve that points back to a hot, denser past. That past is not in a place. The expansion has no centre. Every location was closer to every other location earlier on. Questions often arise. What is the universe expanding into? The balloon tempts us to imagine an outside air, but we should drop that part of the picture. For our universe, the expansion is an internal change in relationships, not a movement into a surrounding box. No edge, no outside wind, just more space between the dots. In that hot early fog, matter and light were partnered in a lively dance. Photons, packets of light, bounced off charged particles so frequently that the universe was opaque. You couldn't have seen your hand in front of your face. When the cooling allowed electrons to settle into atoms, light decoupled from matter, and the universe turned transparent. That fossil light still surrounds us. The cosmic microwave background, a whisper from the young morning. Chemical seeds were sown early. In the first few minutes, when temperatures were like a forge without walls, simple nuclei formed. Mostly hydrogen, some helium, and a trace of lithium. Heavier elements would wait for stars. That first batch is like the pantry staples for a long, slow recipe, stored away until the kitchen gets running. Where did the energy come from? That's a slippery question, because energy in general relativity, our best description of space and time, doesn't behave like coins in a jar. The expanding space can do work on the contents. Light loses energy as its wavelength stretches. Globally, the bookkeeping is subtle. Locally, the rules are clear. Energy and momentum are conserved along paths in space-time. Gravity channels rather than creates or destroys. The Big Bang wasn't loud in any human sense, but it left signatures we can measure. The background glow, the distribution of light elements, and the way structure grew from faint initial irregularities. These independent lines of evidence lock together like the corners of a puzzle. They do not answer everything, yet they draw a coherent picture. A universe that began hot and smooth, then cooled and clumped. Speculative. Before the hot phase, perhaps there was a gentle prelude, a bounce, a prior era, or a field rolling down a hill in a landscape of possibilities. We do not know. What we have is the map from the first frame we can read forward, along with curiosity that refuses to let the trail go cold. So keep the balloon, but keep it honest. No explosion, no centre, no edge. Space expands. Galaxies are carried along like painted dots, mostly following the growth rather than causing it. The beginning is not a bang, but a beginning of relationships, of distances that could change, of rules that would let matter, light, and later life play the long game. And in that game, tiny initial whispers would become the chorus of galaxies lighting the dark. Take a placid lake and sprinkle it with the lightest wind. Ripples run outward, barely there, yet later they decide where leaves gather and where the water stills. In the early universe, something similar happened on the grandest scale. A brief, tremendous stretching called inflation amplified tiny quantum jitters into the seeds of everything. The lake became a sea, and the small became destiny. Inflation is an idea about how very early expansion might have worked. Rather than a steady spread, the universe may have grown exponentially fast for a blink, driven by a high-energy field with peculiar pressure. The image is stretchy dough suddenly ballooning before settling into a gentler rise. In physics terms, a field with nearly constant energy density can make space expand faster than light separates points, not objects racing through space, but space itself growing. Why imagine this? Because it explains puzzles. The cosmos looks remarkably uniform in every direction, like a well-mixed soup. Inflation lets once neighbouring patches grow far apart, sharing the same recipe. Space appears flat on large scales, not curved like a saddle or a sphere. Inflation irons the fabric, and those ripples, the faint, almost scale-free variations, match the patterns we measure in the cosmic microwave background and the distribution of galaxies. Where do the ripples come from? Quantum uncertainty says fields cannot be perfectly smooth. They jiggle. During inflation, the universe stretches so fast that these jigs become frozen as differences in density, like faint hills and valleys in the primordial fog. Later, gravity leans into those hills, pulling more matter their way, while light and pressure push back like springs. The result is a cosmic sound, a pattern we can still hear in the sky's fossil light. We're cautious because we don't know what field drove inflation, or if it happened exactly as the simplest models propose. Speculative. The inflating field might be related to known particles, or to something entirely new, or inflation might be replaced by another early mechanism that solves the same problems. For now, inflation remains the leading sketch that fits many observations with an elegant sweep. One striking promise is the possibility of primordial gravitational waves, ripples in space-time left by the inflationary storm. These would twist the polarization of the microwave background in a very specific swirly way. Experiments in cold deserts and high plateaus point telescopes at the sky to hunt for that subtle swirl. A clear detection would be like finding the footprint of a passing giant. Inflation also softens the worry about initial conditions. You don't need a perfectly tuned birth. Many messy starts slide into the same inflating state, which then resets the table. It's like shaking a snow globe. No matter the details, the flakes settle in familiar drifts. That makes the idea attractive, though not a guarantee that nature chose it. The mathematics behind inflation lives in the gentle language of potentials. Hills and valleys a field can roll along. When the field loiters on a plateau, expansion roars. When it descends and oscillates, energy converts into particles and radiation, a warming afterglow called reheating. Our later universe begins there, hot and busy, with the tiny imprinted ripples left like fingerprints on fresh paint. Critics ask fair questions. Can we test it well enough? Are we inventing too much to patch holes? That scrutiny is healthy. What saves inflation from being a story too eager to please is its quantitative bite. It predicts a near-scale invariant spectrum of perturbations, small non-random deviations measured in the sky. So far the numbers line up. The room for models narrows as data tighten. Speculative. Some versions of inflation never fully end, spawning vast regions with different physics, a multiverse of pocket universes. That concept stretches both imagination and inference. We treat it gingerly, keeping our feet on the most testable ground. The sky we can measure, the patterns we can compare, the signals we can chase with better instruments and cooler detectors. In everyday terms, hold onto the lake with a ripples picture, a hush of quantum jitters blown up to cosmic scales, determined where matter would pile up and where it would thin. Without those fluctuations, no galaxies, no stars, no planets, no us. It is a quiet thought with enormous consequences, The universe's largest features may be the long echo of the smallest possible tremors. Open the oven door and feel a soft wave of leftover warmth after the pie is done. The cosmic microwave background is the universe's leftover warmth, a gentle glow bathing everything from every direction. It's not bright to your eyes, but tune a microwave detector and the sky hums with it, as reliable as the murmur of distant surf. This glow is our oldest picture, a baby photo taken when the cosmos turned transparent. Imagine the early universe as a foggy bath where light keeps bumping into charged particles. Then, as the bath cools, electrons join protons to form neutral atoms, the fog clears, and light can finally travel freely. That release happened roughly 380,000 years after the beginning, and the light from that moment has been stretching with space ever since, drifting from visible and infrared down to microwaves. Today it's about 2.7 Kelvin, just a whisper above absolute zero. Point a sensitive radio telescope anywhere, and you find this glow. It's astonishingly uniform, like a perfectly even paint coat, but not perfectly so. There are tiny temperature variations, tens of microkelvin, mapping slight differences in density and motion back then. Those spots are the fossil ripples inflation promised, and gravity later amplified, the seedbed of structure. A toddler's freckles on the face of the young universe. The glow also carries a pattern of polarization, a subtle orientation of its electric field caused by scattering in the last foggy moments. From that polarization, we can infer the flow of matter and light at the time, and even hunt for the curl signature of gravitational waves from inflation. No detection has stood unchallenged yet, but the search sharpens our ears. The spectrum of this background is almost a perfect blackbody, the characteristic curve of an object in thermal equilibrium. That near perfection is a triumph. It tells us the young cosmos was astonishingly well mixed and thermalized. Any exotic energy injection after that era would have bent the curve. We do not see such bends. The oven was clean. When we measure the detailed statistics of the temperature spots across the sky, a specific pattern emerges, peaks and troughs at particular angular scales. These acoustic peaks are the harmonious leftovers of sound waves in the early plasma, pressure and gravity trading energy like a child pumping a swing. The first peak shows the size of the largest crest that had time to form before transparency. Later peaks trace the interplay of baryons, ordinary matter, dark matter, and radiation. It's cosmic music scored in the sky. From this music we extract numbers, the age and composition of the universe, the curvature of space, the speed of expansion then and now. Strikingly, the data say space is very close to flat on large scales. The mix is about 5% ordinary matter, 27% dark matter, and 68% dark energy. And the Hubble expansion rate has a value that, depending on method, has provoked a lively tension between early and late-time measurements. That tension might be a clue to new physics, or a signal that we've misread some calibrations. We're patient with it. Speculative. There could be subtle relics in the background we've yet to recognize. Fingerprints from decaying particles, a hint of cosmic strings, or whispers of neutrino stories as yet unfinished. So far, simplicity wins, but the sky might be holding a surprise in its pocket. It's worth stressing how impersonal and inclusive this glow is. It doesn't care about planets, politics, or preferences. It arrives in the same way at mountaintop observatories, Antarctic domes, and satellites drifting above weather's reach. If you could see in microwaves, the sky would look like a soft, mottled blanket, comforting in its evenness, humbling in its age. For something so ancient, it remains a modern teacher. Each new map refines our view, shaving uncertainty, revealing tiny anomalies to test. We build cooler detectors to quiet thermal noise, polish mirrors to focus faint patterns, and share the results widely so that many minds can poke at the same riddles. The baby photo is clear, but the family resemblance to later epochs keeps offering lessons. In a quiet hour, remember the oven warmth, the air on your skin after baking, a last cozy breath before the kitchen cools, is a perfect everyday echo of this cosmic relic. The background isn't just a proof of concept, it is the proof of context, the shared backdrop that lets us say with confidence where and how our story began to diversify, brighten, and grow complicated enough to daydream about itself. Scatter a handful of sand on a drum and tap the rim, The grains gather into ridges and nodes, tracing the hidden pattern of vibration. Gravity did something similar after the universe turned transparent. It felt the faint pattern in the primordial fog and drew matter into a vast cosmic web. Filaments, sheets, and knots, with deep, dark voids between. The drum was space. The rhythm came from early ripples. The sand became galaxies. On the larger scales, gravity is patient. It pulls more strongly where there's already a touch more matter, so small advantages snowball. Imagine a shallow dent in a rubber sheet. Marbles roll toward it, making the dent deeper, attracting more marbles. That feedback loop builds filaments linking dense nodes where galaxy clusters form, while the quiet regions grow emptier as matter leaves for busier neighbourhoods. Light plays a counter-melody. In the early plasma, pressure from light resisted compression, much like air pressure resists a piston. Before transparency, that battle set up standing waves, those acoustic oscillations we read in the microwave background. After transparency, gravity largely took the lead, but a fossil of that past push remains in the way galaxies are spaced, a preferred separation scale called the baryon acoustic oscillation. It is a ruler written into the distribution of galaxies. Dark matter is crucial scaffolding in this build. It doesn't interact with light, so it began clumping earlier, without radiation pressure to slow it. Ordinary matter fell into the dark matter's gravity wells later, cooled and formed stars. Without dark matter, the web would be wispy. With it, the network is strong enough to form the luminous islands we see. We can trace the web by several methods. Galaxy surveys map millions of galaxies, sketching filaments and voids like lights outlining streets from an airplane. Weak gravitational lensing measures how mass, visible or not, distorts background galaxy shapes, revealing the web's density like wind highlighting wheat. The forest of absorption lines in quasar spectra shows where tenuous gas lies along vast lines of sight, a tracer of matter between the islands. The story is statistical, not sculptural. We don't predict which exact galaxy ends up where, but we can predict the pattern's overall texture and its evolution across time. Simulations, started with early ripples consistent with the microwave background, grow universes in silico, producing webs, clusters, and galaxy populations that resemble what we see. They also show how feedback from stars and black holes stir and heat gas, altering the details of small-scale structure. Gravity's slow dance shapes more than positions. It sets the stage for galaxy interactions and mergers, triggers starbursts when gas is compressed, and dictates the feeding rates of central black holes. It even affects the rate at which time passes in deep potential wells, a relativistic nuance with tiny but real effects on clocks. The web is not just scaffolding, it's plumbing, wiring, and city planning. Speculative. On the very largest horizons, there might be subtle departures from our simple law of gravity, or whispers of dark matter behaving slightly differently than we assume. Self-interactions, warm speeds instead of cold. Surveys and lensing maps are sharpening their images to catch any such departures, if they exist. Everyday parallels help. Think of frost spreading across a window, branching and linking into delicate lace as it grows. The cosmic web has that branching elegance, though its threads are millions of light years thick. Or think of a railway network built from many small decisions, later forcing traffic along favoured routes. Once the web takes shape, galaxies must travel along its filaments. They rarely cross the empty gulfs. This scaffold also whispers about the universe's expansion history. The way the web grows depends on how fast space expands and what it's made of. Dark energy, the late-time accelerator, slows the clumping on the larger scales. By measuring growth at different epochs, we cross-check the story told by supernovae and the microwave background. When all three agree, our confidence rises. When they don't, we go hunting for leaks in the logic or light in the seams. In the end, gravity's scaffolding is a quiet triumph. From almost nothing differences, a grand architecture arises. The web is spacious and sparse compared to any human city, yet it carries the same feeling of connection, the sense that roads lead somewhere, that junctions matter, that emptiness is as informative as presence. It is the stage on which galaxies perform their long dramas, the unseen hands that nudge the actors into place, and the patient guide that keeps the play coherent across billions of years. Picture an archipelago under a soft dusk, each island with its own weather, music and dialect. Galaxies are archipelagos of stars and gas, each with a character that changes as it lives, moves, and mingles with others. Spirals flaunt grand arms, ellipticals glow like smooth embers, irregulars are scrappy, blue, and busy. Their stories are linked by the web that feeds them, and by gravity's persistent invitations to dance. A spiral is a disk with a thin mist of gas and dust, where new stars spark along arms like streetlights following traffic jams. The arms aren't rigid things, but patterns, density waves where matter lingers, compressing clouds. Bars, straight inner features, can funnel gas inward, feeding central regions and perhaps the black hole. The Milky Way is such a barred spiral, with a halo of old stars and a dark matter cloak. Ellipticals tell a different tale. They are puffier, smoother, redder, with little cold gas left. Many form through mergers, two or more spirals crashing, their stars mixing into a rounded swarm while gas is shocked, heated, and in some cases blown out by starbursts and black hole winds. Their stars are older on average, and their light has a mellow tone, like late afternoon sun through dust. Irregulars are the improvisers. Small and easily stirred, they often live in crowded neighbourhoods, where tides and blows from bigger galaxies bend their shapes. They're rich with cold gas, so they spark with young blue stars and glowing nebulae. They're also common in the early universe, when everything was closer and interactions frequent. Galaxies grow by sipping and by swallowing. They sip gas from filaments, cold streams that thread into their halos like mountain rivers feeding lakes. They swallow smaller galaxies, building their mass and stirring their disks. The gas they gulp is fuel, the gas they blow is feedback, driven by supernovae and black hole jets, which prevents runaway star formation and recycles elements into space. At each galaxy's heart sits a massive black hole, millions to billions of times the sun's mass. When fed, it shines as an active nucleus, sometimes launching jets far beyond the galaxy. Those outflows can heat the surrounding gas, preventing it from cooling too quickly and forming too many stars. It's a thermostat, too quiet, and the galaxy grows bloated, too loud, and the lights go out. We read galaxies' histories through their light. Spectra, the rainbow split by prisms, carry fingerprints of elements, temperatures, and motions. Colour tells us age. Line widths tell us turbulence and rotation. By mapping these properties across a galaxy, we create time-lapse maps of how it formed, a fossil puzzle with pieces painted by starlight. Environment matters. In clusters, galaxies feel tides from their neighbours and the hot fog between them. A spiral diving through that fog can be stripped of gas, a process called ram pressure stripping, quenching star formation and transforming its look. In the field, far from crowds, galaxies can keep their gas longer and form stars at a gentle pace. The cosmic postcode shapes the biography. Speculative. Dark matter's particle nature might tweak small-scale structure, how many tiny galaxies exist, how their inner densities behave. Our counts and lensing hints suggest slight tensions with the simplest cold picture. Warm or self-interacting dark matter could soften cuspy centres, but we're not yet sure. Better surveys and sharper simulations are on the way. Rotation curves, how speed changes with radius, reveal dark matter's role. Stars out in the disk move faster than the visible mass alone can explain. The unseen halo holds them in, like an invisible hand around a spinning pizza. This has been one of the cleaner signs that most mass is dark, gently shaping galactic motions without shining. Galaxies are archives of element making. Early generations of stars forged carbon, oxygen, and iron, then seeded later clouds when they died. Over time, metallicity, the astronomers' term for elements heavier than helium, rises, changing planet formation odds and star colours. Your body chemistry traces a specific galactic history. You carry the flavours of past supernovae. Despite their grand scales, galaxies feel oddly personal. They drift in clusters like families at a picnic, sharing food, bumping into one another, changing plans. Some are quiet readers in the shade, others play loud music and dance. Over billions of years, most go through phases of both. In their variety, we find a mirror for our own communities, diverse, evolving, and connected by flows we mostly sense rather than see. Think of a nursery. Warm, dusty light, soft noise, new lives swaddled and fussing. Stars are born in similar nurseries, cold, dense clouds where gravity and cooling work together to compress gas until it ignites nuclear fires. Their lives are shaped by mass. Heavy stars live fast and die spectacularly. Light stars like the sun burn steadily for billions of years. The endings are beautiful and practical, sowing the elements life needs. A star begins when a patch of a molecular cloud becomes slightly denser than its surroundings, perhaps nudged by a passing spiral arm, or the shock of a nearby supernova. Gravity tugs inward. The clump spins and flattens into a disk. The center grows hot and dense enough to fuse hydrogen into helium. That ignition stabilizes the newborn. Pressure from fusion balances gravity's inward pull. We call this long, steady phase the main sequence. Mass is the clock. A star twice the sun's mass is brighter and hotter, using fuel quickly. A star half the sun's mass is dimmer and longer lived. In the lightest stars, convection, churning motion, stirs fuel efficiently, prolonging lives for trillions of years. The heaviest burn through their reserves in a few million years, like a candle in a gale. As fuel runs low in the core, structure changes. For sun-like stars, the core contracts and heats. The outer layers expand and cool, turning the star into a red giant. Helium in the core ignites, fusing to carbon and oxygen. Later, gentle winds peel away the outer layers, forming a planetary nebula, an expanding, glowing shell, while the core settles as a white dwarf, a dense, Earth-sized ember slowly fading. Massive stars take a fierier path. They build layer upon layer of heavier elements, like an onion, hydrogen to helium, helium to carbon, then to neon, oxygen, silicon, and finally iron. Iron cannot release energy by fusion in such cores. Pressure support fails, the core collapses and a shock rebounds, tearing the star apart in a supernova. The blast forges and flings heavy elements, gold, iodine, uranium into space, enriching future clouds. The collapsed core can become a neutron star, a city-sized object of astonishing density, or if massive enough, a black hole. Neutron stars can spin fast and beam radio waves like lighthouses, pulsars. When two neutron stars spiral together, they create fireworks across the spectrum and launch ripples in space-time we can now hear. These mergers are a major forge for elements like gold. Stars don't live alone. Many form in multiples, and their interactions can swap mass, trigger novae, surface explosions on white dwarfs, or even set up Type Ia supernovae when a white dwarf gains enough mass to ignite catastrophic fusion. Those Type Ia events are standardizable candles, tools for measuring cosmic distances and expansion. Stellar winds and radiation carve their surroundings. Young massive stars blow bubbles in their birth clouds, sculpting pillars and caverns. That feedback regulates star formation, preventing clouds from converting all gas to stars at once. Is a thermostat again, keeping galaxies from burning their fuel too quickly. We read a star's life through its spectrum and position on the Hertzsprung-Russell diagram, a simple plot of brightness and temperature. Clusters of stars show clear sequences and turn-offs that reveal ages. By comparing models and data, we can reconstruct histories and forecast futures, like botanists reading tree rings. Speculative. Some stars may host exotic cores or be influenced by dark matter capture in dense environments, slightly altering their evolution. These effects would be subtle, likely swamped by ordinary physics, but they remind us that stars sit in a wider context. The endings, though bittersweet, are gifts. Supernovae stir and seed the interstellar medium. Planetary nebulae paint delicate shells in space. The calcium in your teeth and the iron in your blood were forged in past stars. When you watch a sunset, you're seeing photons born in a stable stellar core filtered by air, scattering more red than blue. Our days are literally starlight repurposed for comfort. In that sense, stars are less distant ornaments than kin. They give us calendars, harvests, navigation, and a place to send our imagination on nights when sleep is shy. Their births teach patience, their lives teach balance, their deaths teach generosity, and all along physics translates their songs into numbers we can hum, turning awe into understanding without stealing the music. Lay out marbles on a carpet and watch how they settle around furniture and folds. Planetary systems form like that. Dust and pebbles gathering in a disk around a young star, sculpted by gas flows, pressure traps, and migrating worlds. The result is a surprising variety of architectures: hot Jupiters skimming their suns, compact chains of sub-Neptunes, wide cold giants, and rocky worlds with weather as strange as art. The starting set is a protoplanetary disk, a thin, rotating mix of gas and dust. Dust grains stick into pebbles, pebbles into boulders, then into planetesimals, whose gravity accelerates growth into protoplanets. Gas adds drag, guiding orbits and feeding giants if they form before the gas fades. In some disks, dust piles up in rings and gaps, perhaps carved by newborn planets, like sheepdogs herding flocks into lanes. Migration is a key twist. Planets push on the disk pushes back, shifting orbits inward or outward. A giant can plough a gap and drift like a raft in a slow river. Smaller worlds can move in packs, locking into orbital resonances, simple ratios like 3:2 that keep time together. This movement explains hot Jupiters and close-packed systems we didn't expect before we looked. We found thousands of exoplanets by watching stars dim as planets transit or wobble as planets tug. Transit depths reveal sizes, wobbles reveal masses. Together they hint at composition. Some worlds are puffy, with thick envelopes, others are dense, likely rocky or iron-rich. Ensembles reveal patterns, a gap between super-Earths and sub-Neptunes, perhaps sculpted by photoevaporation or core-powered mass loss. Atmospheres are stories in themselves. Light filtering through a planet's air during transit carries spectral fingerprints of molecules: water, methane, carbon dioxide, sodium. With careful, patient observation, we can sketch clouds, hazes, winds, and temperatures. A few hot Jupiters show day-night heat contrasts. A few small worlds hint at volatile, rich envelopes. The detail improves yearly. System architecture matters for habitability and chemistry. A quiet giant far out can shepherd comets, deliver water, or fling hazards. A tight chain of worlds can stir tides and heat interiors, perhaps powering volcanoes and oceans under ice. Tilted orbits, eccentric paths, and multi-star hosts complicate climates in lively ways. Speculative. Some planets could be ocean worlds with global seas tens of kilometers deep. Others could be silicate vapor hells or carbon-rich worlds with diamond rain. There might be planets around white dwarfs warmed by ongoing accretion. There might be moons larger than Mercury with their own atmospheres. We've glimpsed hints, but the catalogue of weird is far from complete. We're also learning how chemistry sets the stage for biology. Disks show snow lines, distances where water, carbon monoxide, and other volatiles freeze, affecting what solids are available to build planets. The mixing and drift of pebbles transport ices inward, salting rocky worlds with water and organics. That redistribution is a quiet act of generosity from the cold to the warm. Planets change after birth. Interiors cool and differentiate. Cores convect and power magnetic fields, shielding surfaces from stellar wind. Plate tectonics reshapes crusts, recycling carbon and regulating climate, though not all rocky worlds have Earth's mobile plates. Impacts deliver and remove, sometimes resetting the clock. The architectures we see challenge our solar system bias. Many stars host multiple close-in mid-sized worlds we lack. Hot Jupiters are rare but striking. Super-Earths seem common. Our layout, small inner rocks, outer gas giants, distant ice, is not the only or even the most frequent melody in the cosmic playlist. In this variety lies a comforting lesson. Nature explores the parameter space with gusto. As we catalogue systems, patterns emerge, but exceptions keep us humble. Each map we draw is a draft. The carpet has more folds and the marbles keep finding them. making arrangements that are both explainable and delightfully unexpected. Imagine a picnic under a mild sun. It's pleasant if the breeze is gentle, the shade dappled, the ground dry. Habitability is like that, a balance of factors, not just distance from the star. The so-called Goldilocks zone is only a starting point. Planetary size, atmosphere, magnetic field, geology and star temperament all tune whether a world can host liquid water and stable chemistry at the surface. Start with energy. A planet too close bakes, too far freezes. But greenhouse gases can trap warmth, extending the range. Clouds can brighten a planet, reflecting light. Surfaces can darken or lighten it. Rotation and tilt distribute heat. A slow rotator under a red dwarf might form a reflective cloud shield on its day side, cooling it enough to be clement. Size matters. Too small, and a planet can't hold on to atmosphere or keep a magnetic field for long. It loses heat quickly and goes geologically quiet. Too big, and it might trap a thick envelope, becoming more like a mini Neptune with crushing pressures. Earth sits in a sweet band where outgassing, volcanism and tectonics recycle carbon dioxide and maintain a thermostat across eons. Water is a player with a dual face. Oceans store heat and moderate climate, but a world covered entirely by deep water might bury its carbon cycle under high-pressure ices at the seafloor, limiting long-term stability. Conversely, a dry world with scattered lakes could still be habitable, with different solutions to climate control. Diversity is allowed. Stellar character is crucial. Sun-like stars are relatively steady. Red dwarfs flare and bathe planets in ultraviolet and particle storms, especially when young. That can strip atmospheres unless magnetic fields and replenishment help. On the other hand, red dwarfs are abundant and long-lived. Many of their planets may find stable niches once the youthful tantrums ease. Atmospheres are both shields and chemistries. Oxygen is not required for life, though it's a striking byproduct of photosynthesis on Earth. Methane, carbon dioxide, water vapour and other gases interplay to shape climate and provide potential biosignatures, patterns that might suggest life's presence. We tread carefully. Many abiotic processes can mimic such signals. Speculative. Life could thrive under ice on tidally heated moons, or in high-pressure seas on super-Earths, or in cloud layers of temperate sub-Neptunes if chemistry and energy flows cooperate. It could use solvents other than water, though water's properties make it especially versatile. We keep minds open while anchoring hopes in the most testable cases. Geology deserves top billing. Plate tectonics helps stabilize climate by cycling carbon between rocks and air. A magnetic dynamo shields against stellar wind. A mix of continents and oceans fosters nutrient cycling. Even the presence of a large moon can matter, taming axial wobble and shaping tides that might encourage coastal ecologies. Time is an ingredient. Habitable is not a snapshot, but a movie. Planets wander through phases, stars brighten, orbits evolve. A world may be habitable early, then lose its air, or start harsh, then soften. We catch them in whatever frame we can, and inference fills in arcs. We test these ideas with models, with observations of exoplanet atmospheres, and with archaeology at home, Earth's own deep past under different suns and skies. Our planet has seen snowball phases, greenhouse bursts, and oxygen's rise. Each era offers analogues for the range of conditions life can tolerate and perhaps prefer. At the picnic, comfort is a mix, and people adjust, seek shade, share blankets, sip water. Worlds adjust too, through cycles and feedbacks. The richest picture of habitability is less a Goldilocks chair, and more a campsite with many workable arrangements. We may find that life, when it appears, is resilient and inventive, making homes in places we once wrote off as too odd. Stretch a bedsheet tight and drop a heavy ball in the middle. Marbles placed nearby roll inward, not because the ball pulls them with strings, but because the surface is curved. That's how to think about black holes. Not monsters with appetites, but regions where space-time is curved so steeply that paths inward are the only options once you cross a boundary called the event horizon. Gravity is geometry. A black hole forms when matter is compressed beyond a critical density, often by the collapse of a massive star's core or by the slow growth of a galactic center feeding for ages. The event horizon is the point of no return, where the escape speed equals the speed of light. Nothing material or immaterial outraces that boundary once inside. Not light, not hope. But outside, the whole simply curves space and time, guiding orbits as surely and predictably as any massive object. From a distance, a black hole is simple. It's described by mass, spin and electric charge, though astrophysical holes are essentially uncharged. Spin matters. It drags space-time around with it, like a whisk-stirring batter, allowing closer orbits and powering jets when magnetic fields thread the swirling accretion flow. These jets can lance out for thousands of light years, influencing their host galaxies. We don't see black holes directly, we see their effects. Gas falling in heats to astonishing temperatures, glowing across the spectrum. Stars near a quiet giant at a galaxy's centre whip around on tight paths. Mapping their orbits reveals a compact mass. Tidal forces near small holes can stretch and tear passing stars, creating flares as debris falls back. Recently, we've even imaged the shadow of a hole, a dark silhouette against glowing plasma. General relativity, Einstein's theory, underlies this. It says mass and energy tell space-time how to curve. Curvature tells matter and light how to move. Near a hole, time runs slower for those close than for those far away. Light redshifts climbing out. Paths bend sharply. Yet the equations don't turn menacing. They are calm, precise, and thoroughly tested in many regimes. At the very edge of understanding lies the interior. Classical relativity predicts a singularity, a place where curvature becomes infinite and the math falters. Speculative. Quantum gravity may replace that with something finite, perhaps a core where space-time's grain matters, or a bounce, or a fuzzed-out horizon. We don't know, and nature hides it well behind the horizon's modesty. Hawking radiation is a theoretical whisper from quantum fields at the horizon. Particle-antiparticle pairs tease energy from the geometry, making black holes slowly evaporate over unimaginable spans for large ones. It's a tiny effect astronomically yet conceptually profound, tying together gravity, quantum theory and thermodynamics. It also raises puzzles about information, how the details of what falls in are preserved or scrambled in the radiation. Careful work suggests no destruction, but the story's fine print is still being written. Black holes are team players in galaxies. Their growth correlates with their host bulges' properties, hinting at a coevolution that runs via feedback. When the hole feeds, it brightens and blasts, heating gas and regulating star formation. When it fasts, the galaxy can cool and grow. The thermostat returns now in the language of jets and winds. Despite their exotic reputation, black holes are not cosmic vacuums indiscriminately hoovering the universe. If our sun were replaced by a black hole of equal mass, Earth would keep orbiting almost unchanged. The drama is local where gravity's curve is sharp. Farther out, it's steady guidance. The best way to make friends with black holes is to keep the sheet and marble picture close and the monster stories at arm's length. They are beautiful solutions to deep equations, clean and compelling, and they give us laboratories for extreme physics we could never build on Earth. In their shadows and waves, we read the fabric's most intimate folds, and in doing so, we learn more about the quiet geometry that holds everything together. Imagine two heavy dancers spinning across a dark stage, the floorboards trembling as they draw close, whirl, and finally embrace. Those tremors are like faint rings travelling outwards across a pond after a pebble drops. Except the pond is space itself. Gravitational waves are ripples in the geometry of space-time, created when massive objects change their motion in abrupt or asymmetric ways. Where sound needs air, these ripples cross the void without a medium, stretching and squeezing everything they pass through by a tiny, tiny amount. That tiny amount is the marvel. The instruments that first caught these ripples, LIGO in the United States and VIRGO in Europe, are giant light rulers. A laser beam is split and sent down two long tunnels, then reflected back by mirrors. A passing wave makes one tunnel effectively a whisker longer, while the other becomes a whisker shorter, changing how the light recombines. The change is so small that measuring it is like noticing the distance to the nearest star change by the width of a human hair. To do this, the mirrors hang on glass fibres, The tunnels are vacuums, and the instruments hum with isolators and controls that make a cathedral of quiet. What do we hear? Mostly the final moments of tight dances between black holes. As they orbit faster and closer, they sing a rising whoop, a chirp, whose pitch and loudness reveal their masses and how fast they spin. When they collide, they merge into a single ringing black hole that settles like a struck bell, the tone again revealing its properties. From these songs we've learned that heavy black holes, dozens of times the Sun's mass, are common in the cosmos, and sometimes they spin in odd ways that hint at turbulent stellar nurseries or dynamical pile-ups in star clusters. Neutron stars, the crushed cores of dead suns, produce a different performance. Their merger adds fireworks, light, neutrinos, and radioactive debris. In 2017, a gravitational wave chirp prompted telescopes worldwide to watch a faint patch of sky brighten and change colour. That event showed where much of the universe's gold and platinum is forged, in kilonova outflows rich with neutron-heavy nuclei. The listen and look approach, called multi-messenger astronomy, has bloomed from that day. Gravitational waves give the beat. Light and particles fill in the instruments. Beyond these dramatic duets, there's a quieter background, like the chatter in a crowded cafe. Pulsar timing arrays, networks of stellar clocks that tick with millisecond regularity, have reported evidence for a low hum likely produced by pairs of supermassive black holes countless galaxies away. As those giants slowly spiral together, they tug space-time with a period of years. It's an exquisitely patient listening game, reading deviations in pulsar ticks across the sky to map a long, slow wave. Future ears will open new registers. The European-led LISA mission, a space-based observatory with laser links between 3 spacecraft millions of kilometers apart, aims to catch gravitational waves at longer wavelengths. Those waves should betray the inspirals of black holes with masses thousands to millions of times the Sun's, and possibly capture extreme whistles from small compact objects falling into much larger ones near galactic centers. On Earth, upgrades to current detectors and new ones like Kagura in Japan will sharpen sensitivity, expanding the reach of our celestial acoustics. These ripples let us test gravity in high drama. Do gravitational waves travel at the speed of light? So far, yes, within tight bounds. Do they lose energy in ways general relativity predicts? Again, the data say yes. We look for hints of dispersion, extra polarizations or deviations in the ring-down tones, signatures that could whisper of new fields or dimensions folded into reality. Speculative. Some theories suggest cosmic strings, ultra-thin, high-tension defects in space-time, might snap and send out distinctive bursts. None have been found, but searches continue. Gravitational waves also give us new yardsticks. Their amplitude tells us distance directly, turning mergers into standard sirens. Pair that distance with a galaxy's redshift and you get an independent handle on the expansion rate of the universe. With enough events and good sky localizations, this may help untangle current tensions between different methods of measuring that rate. All of this rests on exquisite engineering and careful statistics. The signals are faint, the world is noisy. A passing truck, a tremor, even lightning can masquerade as a chirp. Teams build catalogues of artifacts, compare across detectors, and assign confidence through rigorous analysis. The earlier detections came as pairs between facilities thousands of kilometers apart, confirming that nature had played the note, not a local rumble. As sensitivity grows, so does the need to understand subtle backgrounds and the true population of cosmic sources. Listening to space teaches a gentle lesson about perception. We built instruments to hear a register our bodies cannot, and the universe rewarded us with tales of darkness in motion. From the quake of colliding black holes to the hush of a billion slow-dancing giants, the cosmos is not silent. It has rhythms, and we're just beginning to learn the steps. Walk under a city at night and you might notice how the buildings you can't quite see shape the wind. Flags lift, leaves tremble, and currents bend around invisible edges. Dark matter is like that hidden architecture, guiding the motion of stars and galaxies while giving off no light. It is the scaffolding upon which the luminous parts of the universe hang, sensed through its gravity rather than seen with eyes or cameras. The first whispers came from oddities in motion. Vera Rubin and collaborators measured how stars orbit within spiral galaxies and found that their speeds remain high far from the glowing centre, where visible matter becomes scarce. Without extra mass, those outer stars should drift slower. Instead, it was as if each galaxy sat in a massive unseen halo. Earlier still, Fritz Zwicky noticed galaxies in clusters zipping around too fast to be held by the light alone. Put plainly, the visible stuff wasn't enough to account for the gravity on display. Gravitational lensing sharpened the picture. Gravity bends light's path, turning galaxy clusters into cosmic magnifying glasses that stretch and distort background galaxies. Mapping those distortions reveals where mass lies, and again the maps light up in places where there's little visible material. The Bullet cluster provided a striking scene. Two clusters that ploughed through each other, with gas slowed by drag and dark matter floating ahead, traced by lensing. The separation between the gas and the bulk of the mass argues that dark matter passes through itself and ordinary matter with little friction. On the larger scales, the cosmic microwave background, the afterglow of the hot young universe, carries subtle patterns, tiny hot and cold spots that reflect the total matter content. Analyses of those patterns, alongside the way galaxies are distributed today, consistently point to a universe with about 5 times more dark matter than ordinary matter. In computer simulations, when we let this unseen substance dominate gravity early on, filamentary webs of structure blossom in a way that matches the grand layout of galaxies we observe. What is it? The leading picture is humble and broad. Dark matter is cold, moving slowly in the early universe, non-luminous, and interacts very weakly with ordinary particles beyond gravity. That makes it neither stars nor dust nor diffuse gas. Exotic options have long inspired searches. Weakly interacting massive particles, or WIMPs, created in the early fireball, would be perfect fits. Giant underground tanks of ultra-pure xenon, like XeNO, NT and LZ, watch for the tiniest flicker from a rare collision with nuclei. So far, silence. Axions, featherweight particles proposed to solve a puzzle in the strong nuclear force, would gently vibrate in magnetic fields. Experiments like ADMX and HAYTAC listen for their whisper. Again, no confirmed detection yet. The absence of a catch isn't a defeat. It trims possibilities and pushes creativity. Dark matter might be lighter and more wave-like, fuzzy enough to smooth the smallest galactic cores. It could be a mix of particles, or part of a dark sector with its own forces. Some versions allow dark matter to interact with itself slightly, rounding out the dense centres of dwarf galaxies. Warm dark matter, with particles moving a bit faster early on, would suppress the tiniest clumps. Measurements of the Lyman alpha forest, spectral fingerprints from intergalactic gas, put tight limits on how warm it can be. There are also attempts to do without new matter at all. Modified Newtonian dynamics, or MOND, tweaks how gravity behaves at very low accelerations, matching some galaxy rotation curves with fewer inputs. Broader relativistic versions try to handle clusters and cosmology, yet the full suite of evidence, especially lensing maps and the microwave background, remains more naturally explained with unseen mass. The dark matter hypothesis also knits smoothly with how structure forms over time, from early ripples to the rich cosmic web. Indirect searches scan the sky for telltale byproducts of dark matter particles meeting and annihilating or decaying. Gamma-ray telescopes peer into the calm hearts of dwarf galaxies where backgrounds are low. Signals have flirted with significance, only to fade under scrutiny. At the same time, precise measurements of cosmic rays look for unusual patterns among familiar particles. Here too, complexity abounds, with astrophysical sources often stepping in to explain anomalies. On smaller galactic scales, discrepancies prompt refinement. Simulations once predicted overly steep density, cusps at galaxy centres, and too many small satellites. Improved modelling of stellar feedback, winds and supernova pushing gas around, softens cores and disrupts small clumps, bringing expectations closer to what we see. The details matter. The way gas cools, forms stars and explodes, shapes how dark matter rearranges under its quiet pull. If dark matter is the hidden infrastructure of the cosmos, mapping it is like unfolding a city's blueprint. Weak gravitational lensing across wide surveys shows us the mass distribution statistically, revealing where the web is thick or thin. New projects such as Euclid and the Vera C. Rubin Observatory's Legacy Survey of Space and Time will trace this skeleton with finer detail and over wider stretches of space and history. With those maps and clever analyses, we may corner dark matter's properties even without catching a particle in a laboratory. Speculative. Dark matter might be composite, like the protons and neutrons we know, but living in a shadow world with its own dark photons. Or it could be primordial black holes formed from early universe density spikes. Current constraints squeeze these ideas, yet pockets remain where surprises could lurk. Invisible does not mean unknowable. The wind of gravity shows us the unseen structures shaping galaxies and guiding their dance. Each improved measurement, each null result tightens the net. Step by step, the hidden city of the universe comes into focus. Take a stretchy loaf dotted with raisins. As the dough rises, the raisins drift apart, not because they're moving through the bread, but because the bread itself is expanding. That image carries a quiet truth. Space can grow, changing the distances between unbound objects without any rocket push. Dark energy is the name we give to whatever is causing that expansion to accelerate, a gentle hand on the dough that grows stronger over cosmic time. The surprise arrived when astronomers used type Ia supernovae, standard candles whose peak brightness can be inferred, to map how the universe's expansion has changed. They found distant supernova fainter than expected, meaning farther away than simple models allowed. The conclusion, checked against the cosmic microwave background and the scale imprinted by sound waves in the early plasma, the baryon acoustic oscillation, is clear. Expansion speeds up. Gravity, which pulls things together, seemed to be losing a tug-of-war to a pervasive repulsive effect. The simplest explanation is a cosmological constant, an energy density inherent to space itself that doesn't dilute as space grows. Imagine a field of tiny springs everywhere, each with the same gentle tension no matter how much room you give them. In general relativity, this acts as negative pressure, driving acceleration. It sits elegantly in the equations, yet raises an infamous puzzle. Calculations of the vacuum energy from quantum fields overshoot the measured value by an absurd factor. Why is the energy of empty space so small, yet not zero? Because of that discomfort, people have explored alternatives. A slowly rolling scalar field, quintessence, could mimic a cosmological constant while changing over time. Its pressure and energy density would be tied to how the field evolves, potentially leaving fingerprints in the pattern of structure growth. Other ideas take aim at gravity itself, modifying how it behaves on grand scales while keeping the tested success of general relativity near stars and planets. Still others suggest that large-scale inhomogeneities might fool us into thinking there's acceleration when there isn't. So far, when confronted with data across multiple probes, the cosmological constant remains the neatest fit. We track dark energy through a parameter called the equation of state, W, the ratio of pressure to energy density. For a cosmological constant, W equals -1. If W differs from that, or changes with time, dark energy is doing something more dynamic. Surveys like DES, KIDS, and HSC have measured weak gravitational lensing, tiny shape distortions of distant galaxies, to see how structure grows under the combined influence of matter and dark energy. Meanwhile, spectroscopic programs like DESI map millions of galaxies to sharpen the imprint of the baryon acoustic oscillation, providing a ruler that stretches back across billions of years. Tensions in cosmology add spice. One is the differing values of the Hubble constant measured locally, using supernovae and Cepheid variables, versus values inferred from the early universe via the microwave background. Another touches the amplitude of matter clustering S8, where some weak lensing surveys appear to find slightly less clumpiness than extrapolation suggests. These may point to unrecognized systematics, Or they could hint that our model needs a small twist, perhaps a dark energy that evolves subtly, or a sliver of early universe physics we've overlooked. Speculative. A coupling between dark matter and dark energy might alter growth, smoothing some tensions without breaking other fits. Beyond numbers, dark energy affects shapes and flows. Galaxy clusters form more sluggishly in an accelerating universe. Voids grow more dominant. The integrated Sachs-Wolf effect. Photons from the microwave background gaining or losing a tad of energy as they cross evolving gravitational wells offers a delicate check that, so far, aligns with acceleration. On the flip side, precise tests of gravity on solar system and galactic scales keep pressure on modified gravity ideas, many of which invent screening mechanisms to hide changes where we'd notice them most. Fate hangs on dark energy's character. If it is a true cosmological constant, expansion continues and distant galaxies slip beyond our observable horizon, leaving a sparse, quiet future. If W dips below -1, phantom energy, space could rip itself apart in a dramatic finale, tearing galaxies and atoms in a big rip. If W increases over time and flips sign, gravity might regain the upper hand and drive a slow contraction. Most evidence points to the sedate path, but our certainty is bounded by measurement. Speculative. Dark energy could decay into other forms, leaving late-time surprises. Euclid, launched by Europe, joins other wide-field surveys to test dark energy's imprint through lensing and galaxy clustering. The Nancy Grace Roman Space Telescope will extend these measurements from space, free of atmospheric blur. Together with ground-based data from the Vera C. Rubin Observatory, we'll refine W and its possible evolution, cross-check methods, and look for cracks where new physics could peek through. There's poetry in a force that is not a force, an energy that seems most present when nothing else is. Dark energy reminds us that the vacuum isn't nothing. It has character, it shapes history. Whether it's a constant hum or a changing melody, it frames the grandest stories of structure, star, and life. And it nudges a timeless question: how much of reality hides in the calm between the visible things? Think of time like a river seen from a bridge. It looks smooth from afar, yet up close it eddies, rushes, and slows around rocks. Walk down to the bank and dip a stick. Suddenly you feel that flow differently than the person across the stream. Time is the same. We each carry our own clock, ticking along our path through space-time. What we call time dilation is the simple fact that these personal clocks can tick at different rates when we move differently or sit in different gravitational fields. Einstein's insight was to weave time with space into a single fabric, where the speed of light is a universal limit and the laws of physics keep their form for all. That means simultaneity, the idea that two distant events happen at the same time, isn't absolute. Two observers moving relative to each other will slice the loaf of space-time into now and later differently. It's not trickery, it's geometry. The faster you move, the more your time stretches compared with someone at rest. Near a massive body where gravity is strong, time runs slightly slower than farther away. This is not abstract. GPS satellites carry atomic clocks that must account for both special and general relativistic effects. In orbit, they move fast, slowing their clocks a bit, and sit higher in Earth's gravitational field, speeding their clocks a bit. Engineers bake in these offsets so your phone doesn't send you down the wrong street. On Earth, exquisitely sensitive clocks separated by centimetres have measured tiny differences in tick rate due to the change in gravity with height. Time is local and personal, yet reliably linked. Consider the twin story. One travels on a high-speed journey and returns younger than the sibling who stayed home. The resolution lies in the different paths they trace through space-time. One turned around and changed frames, breaking the symmetry. Proper time, the time measured by a clock along its own world line, is the traveller's tally, and different paths tally differently. Near black holes, this difference becomes dramatic. An observer far away watches a clock near the horizon tick ever slower, while the falling clock experiences its own steady march as it crosses into the dark. The arrow of time is a different puzzle. The basic laws of physics mostly don't care which way you run them. They're nearly symmetric if you reverse past and future. Yet we remember the past, not the future. We see eggs break, not reassemble. The thermodynamic arrow points from order to disorder because entropy, related to the number of ways things can be arranged, tends to increase. The crucial ingredient is the universe's start in an extraordinarily low entropy state, a smoothness that defies easy explanation. From that special beginning, gradients drive everything, stars shine, winds blow, life grows, and memories form. Our psychological arrow aligns with entropy's arrow, because brains are physical devices that write records in matter, increasing entropy as they store information. Another arrow, the cosmological one, is the expansion of space itself, giving a backdrop that makes the past look different from the future. Quantum processes add texture. When systems interact with their environment, they undergo decoherence, suppressing delicate superpositions and making outcomes look definite. This too favours a direction, as information leaks into many degrees of freedom. Speculative. Some argue that the arrow emerges from boundary conditions at both the beginning and end of the universe. Evidence is thin, but the debate sharpens our questions. Time also shows up as what clocks measure. The current definition of the second rests on the frequency of light absorbed by cesium atoms, nature's precise metronomes. Newer optical clocks using strontium or ytterbium push precision further, opening tests of physics and new senses for gravity. With them, we can map tiny variations in Earth's gravitational potential, a field called relativistic geodesy, and search for subtle drifts in fundamental constants. Could time loop or allow travel? General relativity admits solutions with closed time-like curves, paths that return to their own past, around exotic structures like rotating cylinders or wormholes. Most physicists suspect that nature blocks these in practice, perhaps through quantum effects that destabilize would-be time machines. Speculative. The chronology protection idea that physics prevents paradoxes has no formal proof, but it's a comforting hunch. On human scales, we feel time stretch and squeeze emotionally, but the physics remains steady beneath our days. We age because complex biological systems accumulate change. We measure durations because regular processes give us reference beats. Sit near the sea and watch the tide, slow, relentless, nuanced by the moon. Our lives ride a richer tide set by thermodynamics, gravity, and motion. The gift of relativity is not to make time strange, but to make it honest. It tells us our tick is ours, that others' ticks are theirs, and that the way we move and where we rest matters. It shows that the universe's arrow is woven into the conditions that made stars and us. Although we can imagine slipping the arrow, we live within it, gathering meaning along the flow. Picture a still paddock at dawn, the grass heavy with dew that trembles when a breeze passes. Think of that dew-laden field as a set of invisible seas, each one filling space. Quantum physics says the world is built from fields like these, one for electrons, another for photons, and so on. Particles are ripples in those fields, the way a breeze can raise a ripple in the grass. The quiet isn't emptiness either. Even in its lowest energy, each field jitters slightly, and those jitters sometimes leave fingerprints. Uncertainty is the first gentle hint. It's like trying to take a perfectly sharp photo of a bird in flight while also nailing its speed. You can't have both perfectly at once. In quantum terms, certain pairs of properties resist simultaneous precision. This doesn't come from clumsy instruments. It's built into how the world is put together. That finite fuzziness underlies the stability of atoms and the chemistry that follows, a steady background hum to our everyday solidity. Entanglement is stranger yet, though it can be pictured like a pair of coins forged together. Flip them apart and they still add up in a set way. If one lands heads, the other must be tails. No matter how far they've flown, quantum pairs go beyond coins, correlating outcomes in ways that can't be mimicked by any shared instruction, set laid down in advance. Repeated experiments, Bell tests, have shown this, closing loopholes with fast switches and distant detectors. No messages fly faster than light. Instead, the joint state is a single book that only appears as 2 pages when read. The vacuum's jitters are not idle. The Casimir effect, 2 uncharged metal plates placed very close together, reveals a tiny attraction that arises because some field ripples fit in the gap and others don't. In curved space-time, the vacuum can become productive. Near a black hole, quantum fields allow radiation to escape, slowly bleeding the hole's mass in what we call Hawking radiation. In an expanding universe, the stretching of space can freeze quantum fluctuations into classical seeds, the faint initial variations that grew into galaxies. Double-slit experiments distill quantum ambiguity into a fingertip feel, send particles one by one through two open paths, and the pattern on a distant screen builds up as if each particle had explored both routes and interfered with itself. Add a which-way detector, even a whisper of information, and the pattern changes. The act of making information available reshapes outcomes. Decoherence explains much of this. Interactions with the environment entangle delicate superpositions with many degrees of freedom, so that interference fades and classical-looking alternatives emerge. Yet the measurement problem remains, a philosophical knot around what, if anything, collapses. Speculative. Some interpretations say the wave function never collapses. Every possible outcome happens in a vast branching multiverse, while others imagine hidden variables guiding particles along definite paths. Objective collapse models, meanwhile, propose that superpositions spontaneously break beyond some scale. None change day-to-day predictions where they overlap. They differ in story, and perhaps in subtle experimental consequences people are beginning to chase. Quantum fields supply a common language. Photons are excitations of the electromagnetic field. Electrons ripple in their own field and carry charge. The Higgs field, pervading space, gives mass to some particles by resisting certain motions. We can create and annihilate quanta in laboratories, manipulating light in cavities and atoms in traps, testing the rules with exquisite control. Those same rules are capable of producing entanglement across kilometers of fiber, or between satellites and ground stations, seeding a nascent quantum internet. Quantum information thinking reframes the oddities as resources. Entanglement becomes a currency for teleporting states, not matter. Uncertainty bounds what can be known and compressed. Error-correcting codes protect fragile quantum bits from noise. Quantum sensors use interference to measure tiny accelerations, rotations and fields, improving navigation and probing geophysics. Optical lattice clocks, ticking with astonishing steadiness, turn quantum transitions into timekeeping better than any pendulum could dream. At cosmic edges, quantum hints poke into gravity. Black hole thermodynamics links area, entropy and temperature in a way that suggests space-time has microscopic degrees of freedom, like atoms of geometry. The holographic principle proposes that information in a volume can be encoded on a boundary, a radical reshaping of where reality lives. Speculative. Some pathways toward quantum gravity imagine space emerging from patterns of entanglement itself, the way a net emerges from knots. Though quantum physics can feel uncanny, its touch is everywhere. The colour of the sky, the sharp lines in sodium lamps, the silicon heart of your phone, the MRI images of a beating heart, all hum with quantum rules. If we start from waves on a dew-bright field, then admit that some waves come paired and some remain inevitably fuzzy, the strangeness softens into a different kind of common sense. The world is not clockwork. It's a symphony, with notes that can harmonise across distance, and with silences that still contain a pulse. Imagine a campfire at the end of a long night. The flames have shrunk to embers. The logs glow and then darken. Warmth leaks into the cool air. The universe's long future looks a bit like that. No dramatic bang, just a deep, slow fade. In the standard picture, stars form, shine, and eventually stop forming. Galaxies grow tired. Gravity and quantum rules keep working, but the grand, bright things give way to quiet. Stars won't last forever. The gas that fuels them will be used up or locked into remnants. In a few trillion years, the last red dwarfs will flicker out, leaving behind white dwarfs, hot, dense cores that slowly cool. Some will crystallize, becoming cosmic diamonds under immense pressure. Planets will become orphans, ejected by gravitational encounters or drifting as their stars die. Galaxy groups will merge under their mutual gravity, forming swollen giants surrounded by thin halos of wandering stars. Black holes will dominate. Over stupendous times, they will swallow nearby matter and smaller black holes growing heavier. Yet even they leak energy through Hawking radiation, glowing faintly in wavelengths longer than the size of galaxies. A black hole with the mass of the Sun takes far beyond any current era to evaporate. Supermassive ones take longer still, their lifespans dwarfing any number the mind readily holds. Eventually, though, even these titans will be gone, leaving a sea of ever-bitten particles and low-energy radiation. The details depend on physics still unsettled. If protons decay, a possibility allowed by some theories' unifying forces, then matter itself slowly dissolves into lighter particles, hastening the fade. If they don't, matter hangs on as white dwarfs and black dwarfs for unimaginable spans. Speculative. There might be rare black dwarf supernovae when some massive black dwarfs undergo pycno-nuclear reactions and detonate, adding a last glitter to the dark. Dark energy adds another slow twist. As expansion accelerates, distant galaxies peel away over the horizon, their light redshifting into oblivion. Future observers, tucked in a bound island, would see a lonely cosmos. No cosmic microwave background, no external galaxies, just the fossil light of their own stars and the physics they can recreate. Knowledge itself would become parochial, a reminder that we live in a privileged dawn when the sky still declares its history to us. Other fates have been imagined. If dark energy grows more intense with time, pulling with ever-increasing ferocity, structures could be torn apart in a big rip. First galaxy clusters, then galaxies, then stars, then planets, and finally atoms. If dark energy were to change sign or new physics were to quench acceleration, a slow reversal might begin, leading to a big crunch, a reheating, and perhaps a new cycle. Current evidence favours the slow fade, but the door is ajar. Speculative. Vacuum decay. Our universe's vacuum slipping to a lower energy state would send a bubble racing out at light speed, rewiring the laws of physics in its wake. There'd be no warning. It's a thought experiment with no actionable dread. Even in the quietest future, processes continue. Gravitational interactions eject stars from galaxies. Binary orbits decay via gentle gravitational waves. Cold matter clumps into dark, diffuse structures. Neutrinos, the shy particles everywhere around us, carry a thin echo through the darkness. Black holes, while they last, write poetry in gravity, ringing as they merge and whispering radiation as they fade. Timescales here are beyond clocks and calendars, beyond metaphor. It's enough to say that the universe is patient. What matters to us is that the present is lush. There is gas to make stars, stars to make planets, planets with oceans and rock and ice, and minds that can ask how it all ends. That curiosity lights a candle against the grand cool. In knowing the ember's future, the blaze of now feels warmer. This fate, whatever its flavour, brings humility. The universe does not owe its drama to our attention, and yet we find ourselves in a chapter that's readable and bright. From that vantage, the distant future is not tragedy, but an epilogue written in faint ink. It will be all right that no one is there to read it. What matters is that the story allowed readers a tool. Imagine opening a well-kept toolbox. Each tray holds a different instrument, each suited to a task. Astronomy is like that. We don't have one magic lens, but a kit of tricks that lets us read light, gravity, and particles to infer what's out there. Every tool has quirks. Used together, they make a sturdy picture. Light is our primary messenger. Telescopes gather it from radio waves to gamma rays, each band revealing different physics. Radio dishes catch the whisper of hydrogen clouds and the roar of pulsars. Infrared eyes see through dust to nurseries where stars are born. Optical and ultraviolet telescopes map stellar populations and exploding stars. X-ray and gamma-ray instruments reveal hot gas, black hole accretion, and cosmic rays. Each photon carries energy, direction, and timing, breadcrumbs back to its source. Spectroscopy splits light into a rainbow, turning hue into numbers. Dark absorption lines mark elements in a star's atmosphere. Bright emission lines highlight gas lit by shocks or radiation. Shifts in those lines reveal motion. towards us or away, fast or slow. Redshift measures expansion on grand scales. With spectra, we read temperatures, densities, compositions, and velocities. Combined with images, spectra turn pinpricks into places. Distances are stitched together with a ladder. Parallax, the apparent shift of nearby stars against distant ones as Earth orbits, anchors the first rung. Cepheid variables and type Ia supernovae, whose intrinsic brightness can be inferred, extend the reach to distant galaxies. The Baryon acoustic oscillation imprint supplies a standard ruler across history. Each rung has uncertainties. Overlap between them checks for errors and biases. Gravitational lensing bends not light's colour but its path. Massive objects act as lenses, sometimes producing multiple images, arcs or rings. Strong lensing that can magnify and probe distant galaxies in detail. Weak lensing is subtler, an ensemble effect that slightly stretches the shapes of many background galaxies. By measuring those tiny shears statistically, we map the foreground mass, including dark matter. Lensing is both a microscope and a scale. It brightens and it weighs. Interferometry uses distance itself as a lens. By linking telescopes across kilometres or continents, we synthesize a virtual telescope as big as the separation between dishes. That sharpness gave us the first images of a black hole's shadow and resolves the surfaces of stars. At radio wavelengths, arrays like ALMA and the very long baseline interferometry network paint disk structures around newborn stars, tracing where planets may be forming. Particles beyond photons widen the kit. Neutrino observatories buried in ice or water catch the faint flashes from these near massless travellers, offering peeks into nuclear furnaces and stellar explosions. Cosmic ray detectors read the fallout of high-energy collisions. Gravitational wave observatories, as described earlier, translate space-time stretch into distance changes. Multi-messenger astronomy blends these channels, cross-validating models and breaking degeneracies that light alone can't. Inference is the quiet craft that ties observations to understanding. We build models of stars, galaxies, cosmology, and ask what parameters best fit the data. Bayesian methods let us incorporate prior knowledge and quantify uncertainty, producing not a single answer, but a range of possibilities. Simulations test whether our models can grow structures like we see. Mock catalogues reveal biases introduced by selection effects and measurement noise. We calibrate, cross-check, and iterate. Every measurement sits in a web of systematics. Instruments drift, atmospheres blur, detectors have quirks, surveys sample what they can see, not what exists in perfect proportion. Good practice is forensic. Track every assumption, propagate errors, perform blind analyses to avoid unconscious nudges. Reproducibility matters. Independent teams and independent methods make the same claims more credible. Null results, no detection, are data too shrinking the space of the possible. People and software are partners. Pipelines handle torrents of data. Machine learning spots patterns faster than any human could, and yet human insight frames the questions and sniffs out the too good result. Citizen scientists help classify galaxies and search for gravitational lenses, an army of curious eyes that still beat algorithms in some tasks. Open data policies turn solitary hunts into communal projects, enabling discoveries that weren't planned when the observations began. The kit grows. Euclid, the Rubin Observatory, the Roman Space Telescope and more will fill plates with deep surveys, precise spectra, and time series data. New detectors will listen for neutrinos and gravitational waves with greater sensitivity. Laboratory astrophysics tightens links between line lists and actual spectra. Ground truth and sky truth converge, step by patient step. How we know is less a badge than a practice. Be curious, be careful, be transparent. It is a culture of checks, of joy in being wrong in the service of getting it right. The universe is under no obligation to be simple, but it is lawful. With the right tools, used humbly, we can read those laws off in reflections, whispers and shadows. Stand in an open field and look around. There's no special spot where the middle of the field sits. Wherever you stand, the horizon looks much the same. The universe is like that on large scales. There is no centre where the Big Bang happened and no edge where everything started spilling out. Instead, every region of space was once closer together, and space itself has been expanding ever since. The balloon picture helps if handled gently. Draw dots on a balloon and inflate it. Each dot sees the others recede, and none sits at the centre of the surface. Our universe isn't the surface of a balloon, and it isn't expanding into anything outside. But the core idea travels well. Distances grow because space grows. That's why distant galaxies show redshifts proportional to their distance, not because they're tearing through space away from a central blast, but because the fabric between us and them stretches. Bound structures don't feel this stretch. Your house doesn't expand with the universe. Neither does the solar system nor the Milky Way. Local gravity, electromagnetic forces, and chemical bonds hold those together. Expansion matters over vast intergalactic scales, where no binding forces oppose the subtle drift. Thinking otherwise leads to the feeling that something's wrong, because tape measures aren't growing in our hands. They aren't. The metric that defines distance between unbound galaxies is. Another confusion hovers around the word explosion. The Big Bang was hot and dense everywhere, not a fireball in one spot. It's more like every point a long time ago was close to every other point, and then the whole lot expanded and cooled. There was no centre to fly from. There was an initial condition baked into the fabric of space-time. Asking what it expanded into is like asking what's north of the North Pole. The coordinate chart runs out. People also wonder about the edge. The observable universe has a horizon because light takes time to arrive, and because space itself stretches the paths light takes. We can't see farther than the distance light has had time to cross since the early plasma became transparent. That's a limit of access, not a physical wall. Beyond our horizon, more universe likely continues with much the same large-scale look. Speculative. If space is finite, it could wrap around in a way that eventually brings a traveller back to a starting point, but on scales larger than we can currently probe. Redshift itself invites misreadings. It's not tired light losing energy through some cosmic friction. It's the stretching of the light's wavelength as space expands. Some argue for alternative mechanisms, but they stumble on observations. How time dilation shows up in distant supernova light curves, how the cosmic microwave background spectrum is a near-perfect blackbody, how large-scale structure lines up with an expanding framework. The expansion model knits these phenomena into a single cloth. As for motion versus expansion, it helps to separate the two. Galaxies move through their local patch under gravity, peculiar velocities, which can add to or subtract from the redshift. On small scales, this produces patterns like the fingers of God in redshift surveys, where clusters appear stretched along the line of sight due to member galaxies' internal motions. On large scales, the coherent pattern of expansion dominates, and the peculiar motions average away. Do we live near the centre of something? Observations show the universe looks roughly the same in every direction, isotropic, and from different places, homogeneous, at large scales. If we sat near a special centre, we'd expect telltale patterns, dipoles and gradients beyond those due to our own motion, that don't appear. The cosmic microwave background acts as a check. Its tiny temperature fluctuations match expectations from a smooth near-flat universe, with no off-centre weirdness required. Another common thought: if the universe is infinite, how can anything be rare? In an infinite expanse, every allowed arrangement occurs somewhere, but that doesn't make unlikely things common where we are. Probability remains local, a reflection of what we can reach and sample. Speculative. Multiverse ideas extend this, positing regions with different physical constants, or vacuum states born from eternal inflation. These remain conjectural, interesting as frameworks but awaiting sharp tests. Finally, the word nothing causes mischief. In physics, vacuum has properties, energy and structure. When we say the universe came from nothing, we usually mean not from pre-existing space and time as we understand them. That's a verbal shortcut, not a claim that things popped out of literal non-being. It's better to say the early universe was a hot, dense, rapidly changing state, whose deeper origin is still under study. Let the field image return. No spot is the centre. The edge is just the limit of what your eyes can reach in the mist. someone else, far away, sees their own horizon. The sky's story coheres when we give up the search for a privileged place and accept that we are typical on the grandest scales, yet unique in our small corner. Picture a forest at first light. Mist lifts, birds test their voices, and a chorus grows from many small beginnings. Life in the universe feels like that, a gathering of chemistry and time, with conditions gradually tuning themselves to support complexity. We are made of stardust not as poetry but as plain fact. The carbon in our cells, the calcium in our bones, the iron in our blood were forged in stars and scattered by their deaths. Planets catch that debris and offer surfaces, seas and atmospheres where chemistry can get to work. Habitability is more than a quiet orbit in a Goldilocks zone. It includes a planet's size and composition, a magnetic field to deflect charged particles, plate tectonics to recycle nutrients and stabilize climate, and a star that behaves kindly. Oceans, continents and atmosphere create feedback loops that can maintain liquid water over long spans. Moons matter, impacts matter, chance matters. Variety across thousands of exoplanets shows nature's creativity. Hot Jupiters skimming star surfaces, super-Earths with thick blankets of gas, ocean worlds, and likely rocky planets with weather we can only imagine. Life's origin is still a detective story. Did it spring from warm ponds rich in organics and cycles of wetting and drying that favoured polymers? Did it emerge at hydrothermal vents where rich chemistry and energy gradients abound? Laboratory work shows pieces of the puzzle. Amino acids, nucleotide precursors, and membranes can form under plausible early conditions. RNA can both store information and catalyze reactions, earning a central role in many scenarios. Speculative. Life might also start in places we haven't yet considered, like within porous rock or in ice that concentrates reactants during freezing. Once life begins, evolution explores the landscape. On Earth, microbes reigned for most of the planet's history, transforming the atmosphere with oxygen, building stromatolites, and sponsoring symbioses that led to complex cells. Multicellularity arose more than once. Eyes evolved multiple times. Intelligence is one branch among many. The contingency of it all argues against inevitability, yet the robustness of chemistry argues for abundant, simple life wherever conditions are stable. Detecting life elsewhere means looking for whispers on distant air. Biosignatures could include oxygen paired with methane, which would otherwise destroy each other, or patterns of gases that suggest ongoing metabolism. Surface colours might betray vegetation-like pigments. Time variations could indicate seasons. Instruments like the James Webb Space Telescope already sniff atmospheres of some exoplanets. Future observatories hope to isolate Earth-like planets' light from their stars' glare to read their skies directly. Technology might leave louder traces: radio emissions, laser flashes, industrial chemicals in atmospheres, night-side illumination, or megastructures that alter a star's light curve are all discussed. So far, searches for technosignatures haven't found a clear signal, but they've only just begun to cover the haystack. The Drake equation frames the question by multiplying probabilities along the path from star formation to communicative civilization. It's a compass, not a calculator. The Fermi paradox, if life is common, where is everyone, invites many answers. Civilizations might be rare, short-lived, quiet, or uninterested in announcing themselves. Space is vast, signals faint, and time windows misaligned. Speculative. A great filter could lie behind us, making our origin rare, or ahead of us, making longevity difficult. Or perhaps, more prosaically, we've barely begun to look with the right tools and at the right frequencies. Mind emerges from matter. Brains are organs that transform energy and matter into patterns that predict, feel, and plan. Consciousness, whatever else it is tied to biological processes that can fail, recover, and change. There's no recognized line where atoms suddenly switch on awareness. Instead, there are layers: sensation, integration, memory, self-models, built atop old scaffolds. Speculative. Conscious experience may relate to particular kinds of information integration. Theories differ, and tests are hard, but they sharpen our language. Life and mind feed back into the cosmos. Technological species rework their planets, changing atmospheres and biospheres. They can send probes to other worlds, link minds through networks, and eventually perhaps engineer on stellar scales. With power comes responsibility. A civilization that lasts must learn to live within planetary boundaries or extend them gently, to value stability as much as expansion. It's a comfort to picture the cosmic forest. Dawn is not a guarantee of noon, but the light is real. We are one bird among many possible, our song shaped by physics and history. Whether we are early or late, common or rare, the fact of our awareness stitches a local thread into the universe's fabric. That we can ask these questions is itself a sign of something flourishing. Take a deep breath. There's a hush in reflection, like the still air after rain when colours seem freshly painted. Humility, hope, and wonder are not lofty decorations. They're practical attitudes that keep curiosity honest and joy alive. Humility reminds us that most of reality does not need our permission to be as it is. Hope invites us to keep working, even when answers hide. Wonder holds the door open. Because what's beyond is often bigger than we think, humility shows up in the way we handle unknowns. Dark matter and dark energy are placeholders for effects we can measure but not yet explain. That isn't failure. It's a map with blank regions marked to be explored. It takes humility to let data lead, to admit when favoured hypotheses don't survive contact with the sky. It takes humility to know that our instruments are always imperfect, our models always provisional. The reward is sturdier knowledge and fewer regrets. Hope is the thread between generations. A child who looks up and asks why is tied to millennia of stargazers, navigators, healers, and tinkerers. Engineers who polish mirrors larger than houses, technicians who tend detectors that can sense emotion smaller than a proton's width, coders who wrangle petabytes. All are builders of hope embodied in hardware and code. Teachers and communicators pass torches. Caregivers make space for minds to grow. Hopeful work is cumulative. It banks progress that others can spend on fresh risks. Wonder is personal and collective. It happens when a backyard telescope lands Saturn's rings in your eye, when an aurora treads green across the night, when a graph on a screen suddenly lines up with a theory scribbled the evening before. It happens in museums and bushwalks, in late-night chats and quiet libraries. Wonder isn't naive. It's aware that awe and critical thought can share a room. To feel the sweep of a galaxy, and then ask what the data say is to be properly human. Gratitude deserves a place. The sciences of the sky rest on lands cared for by indigenous peoples, whose knowledge of the heavens runs deep. Observatories rise where the air is thin and clear. Those places have histories and communities deserving respect, partnership, and benefit. Credits are more than lists of names. They are acknowledgements of labour, culture, and place. The universe belongs to no one, but our ways of meeting it should honour everyone involved. Credits also flow across disciplines. Physics leans on mathematics, astronomy leans on chemistry and geology, cosmology leans on philosophy's careful questions. Art helps visions land in hearts. Journalism and public service keep the civic space where science can thrive. The web of contributors is thick and often invisible. Administrators, cleaners, drivers, cooks, parents. Behind every crisp image of a nebula is a bus schedule that ran on time. There's a tenderness in looking outward and inward at once. The sky is not an escape from earthly cares. It's a reminder of context that can make cares lighter to carry. When we learn that everything we touch is stardust, we often become gentler with rocks, rivers, and other people. The perspective doesn't erase pain or injustice. It steadies the hand that works against them. The long view can feed the short action. What do we do with this knowledge? We can teach it, share it, and let it colour our choices. We can build cities that waste less light, leaving darker skies for everyone. We can support libraries, museums, and classrooms as spaces where wonder is normal. We can fund the next generation of observatories with both public money and public trust. We can remember that error bars are not flaws, but evidence of care. We can also sit quietly and look up. There's no requirement to turn every star into a calculation. A human being resting under the Milky Way is enough. The mind will do what it does. Connect, compare, compose. In those moments, humility, hope, and wonder braid themselves without fuss. If you'd like more quiet explorations like this, consider subscribing, and if you have a moment, share where you're listening from and the time. In closing, a soft thank you to everyone who keeps curiosity alive: researchers and readers, observers and thinkers, elders who remember, children who insist on one more question. May we keep tending the night, so that when we look up we still feel at home.